Hello, and welcome to this presentation of the Flexible Datarate Controller Area Network Interface. It covers the main features of this interface, which is widely used to connect the microcontroller to a CAN network. The Flexible Datarate Controller Area Network, or FDCAN, is a standardized serial differential bus broadcast interface that allows a microcontroller to communicate with external devices on the same network bus. The FDCAN interface is highly configurable, enabling nodes to connect using only 2 wires. Applications benefit from several features. A multi-master concept with message prioritization. Object-oriented communication, which uses content identification instead of node addressing. Real-time capability with low message transfer latency. System-wide message consistency, with built-in error detection and management mechanisms. The STM32C0 microcontroller integrates one FDCAN controller. The CAN subsystem supports one FDCAN controller, named FDCAN1. This controller supports both the basic extended CAN protocol, versions 2.0a and b, with a maximum bit rate of 1 megabit per second, as well as the CAN FD protocol version 1.0, with up to 64 data bytes and a data bit rate of up to 8 megabits per second. The CAN core contains the protocol controller, as well as receive and transmit shift registers. It handles all ISO 1189-91-2015 protocol functions and supports both 11-bit and 29-bit identifiers. The TX handler controls the message transfer from the message RAM to the CAN core, while the RX handler controls the transfer of received messages from the CAN core to the external message RAM. 2 clock domains are implemented: the APB bus interface and the CAN core kernel clock, and therefore synchronization blocks are required between these 2 domains. A shared 0.8 kilobyte message RAM memory is available. This RAM is used to contain the filters, buffers, and FIFOs. The CAN subsystem input and output signals and pins are detailed in this table. 2 clocks are provided to the FDCAN unit. FDCAN CK, the kernel clock used to obtain the bit rate. FDCAN APB, which is the APB clock used to access memory-mapped registers and message RAM. 2 interrupt outputs enable the FDCAN unit to report events to the Cortex M0 Plus core. An external 16-bit timestamp input port can be used by the FDCAN unit to timestamp the transmission or reception of a message. This timestamp is provided by a timer contained in the FDCAN block. FDCAN RX and FDCAN TX have to be connected to the transceiver. Lastly, the APB slave interface is internally split into 3 parts, each having a dedicated chip select, configuration, control, and RAM access. The FDCAN controller conforms with the CAN protocol version 2.0, parts A and B, ISO 1189-91-2015, as well as the CAN FD protocol with a maximum of 64 data bytes supported. The maximum bit rate in FD mode is 8 megabits per second. Each controller also supports 2 independent maskable interrupts, each with 24 fully configurable interrupt flags. The controllers have a power-down mode and support error logging, AUTOSAR, J1939, and separate signaling upon reception of high-priority messages. Up to 3 received messages can be stored in each of the 2 RX FIFOs. The acceptance filter selects which FIFO to use. Up to 3 messages to transmit can be stored as part of the message RAM, configured either as a TX FIFO or as 3 separate TX buffers. Each entry of the RX FIFO and TX FIFO, or TX buffers, supports the maximum message size of 64 bytes of payload. The TX event FIFO stores TX timestamps along with the corresponding message ID. There are two variants in the FDCAN protocol: long frame mode, or LFM, where the data field of a CAN frame may be longer than 8 bytes, up to 64 bytes. Fast frame mode, or FFM, where the control field, data field, and CRC field of a CAN frame are transmitted at a higher bit rate compared to the beginning and the end of the frame. This high data rate is typically 8 megabits per second. Fast frame mode can be used in combination with long frame mode. The bit timing logic monitors the serial bus line and performs sampling and adjustment of the sample point by synchronizing on the start bit edge and resynchronizing on the following edges. The time quantum is the basic timing unit, obtained from the configuration unit and equal to FDCAN TQCK multiplied by a ratio from 1 to 512, programmed in the FDCAN NBTP register. The bit time is split into 3 segments: the synchronization segment, bit segment 1, and bit segment 2. Each of these segments is an integer multiple of the time quantum. The duration of BS1 and BS2 is independently programmable for nominal bit time and data bit time. The data bit time applies when operating in FD mode, and data are transmitted at the high data rate. In order to adjust the on-chip bus clock, the CAN controller may shorten or prolong the length of a bit by an integral number of quanta. The maximum value of these bit time adjustments is termed the synchronization jump width, or SJW, which is programmable from 1 to 4 time quanta. The transmitter delay compensation enables configurations where the data bit time is shorter than the transmitter delay. It is enabled by setting the TDC bit in the DBTP register. The received bit is compared against the transmitted bit at the secondary sample point SSP. The SSP position is defined as the sum of the measured delay from the FDCAN transmit output pin, FDCAN TX, through the transceiver to the receive input pin, FDCAN RX, plus the transmitter delay compensation offset. The transmitter delay compensation offset is used to adjust the position of the SSP inside the received bit, for example, at half of the bit time in the data phase. The FDCAN has 3 main operating modes: initialization, normal, and sleep. After a hardware reset, the FDCAN enters initialization mode via software. In this mode, the peripheral must be configured, including bit timings and RAM allocation. In the bit timing configuration, the rate is set, and the sampling point is adjusted according to the actual serial bus line. The CAN controller then synchronizes itself with the CAN bus by waiting for 11 consecutive recessive bits. When the CAN is in normal mode, the user can select different specific submodes. Classic CAN mode, compatible with CAN specification. 2.0b. FDCAN mode. It can be long frame and or fast frame mode, named respectively LFM and FFM. Restricted mode. The controller is able to receive data frames and acknowledge them, but does not send frames. It can be used in applications that adapt to different CAN bit rates. Bus monitoring mode. The controller is able to receive data frames but cannot acknowledge them. It can be used to analyze the traffic on a CAN bus without affecting it by the transmission of dominant bits. Test modes are detailed in the next slide. Upon a CPU request, the FDCAN is put in sleep mode, which operates at a lower power when the bus idle state is detected. To enable write access to the FDCAN test register, the test bit in the CCCR register must be set to 1, thus enabling the configuration of test modes and functions. In test mode, Software can control the state of the FDCAN TX pin and can read the state of FDCAN RX. Through the FDCAN test register, software can control the FDCAN TX output, force dominant level, force recessive level, and monitor the sample point. The actual value at pin FDCAN RX can be read from the RX bit in the FDCAN test register. Both functions can be used to check the CAN bus physical layer. These test modes should be used for production tests or self-tests only. Furthermore, the FDCAN controller supports two loopback modes that are entered through control bits in the FDCAN test and FDCAN CCCR registers. In external loopback mode, the FDCAN treats its own transmitted messages as received messages and stores them, if they pass acceptance filtering, into RX FIFOs. This mode is provided for hardware self-test. In loopback mode, the FDCAN controller is designed to operate independently from external communication. It achieves this by disregarding acknowledgement errors, which occur when a recessive bit is sampled in the acknowledgement slot of either a data or remote frame. This allows the controller to focus solely on internal operations without being influenced by external network conditions or acknowledgement feedback. Internal loopback mode can be used for a hot self-test, meaning the FDCAN can be tested without affecting a running CAN system connected to the FDCAN TX and FDCAN RX pins. In this mode, the FDCAN RX pin is disconnected from the FDCAN, and the FDCAN TX pin is held recessive. The FDCAN controller offers the possibility to configure two sets of acceptance filters, one for standard 11-bit identifiers and another for 29-bit extended identifiers. Each filter element is configurable for acceptance or rejection filtering. Each filter element can be enabled or disabled individually. Filters are checked sequentially, and execution stops with the first matching filter element. Software configures the number of active filter instances. The maximum is 28. Acceptance filtering is started after the complete identifier has been received. After acceptance filtering has completed, and if a matching RX FIFO has been found, the message handler starts writing the received message data in 32-bit portions to the matching RX FIFO. Each filter element offers flexible configuration options, allowing it to function as a range filter, specifying a from-to range, a filter for one or two specific message IDs, or a classic bit mask filter. When dealing with extended IDs, the extended ID and mask, or XIDAM, is applied using a logical AND operation with the incoming identifier before the filtering process begins. To filter for a specific message ID, the filter element must be configured such that both SF1 ID equals SF2 ID and EF1 ID equals EF2 ID. This algorithm describes the filtering sequence of frames received with a standard ID. A similar approach is used for extended ID frames, though the configurations for each are handled independently. The process begins with the decision to either accept or reject remote frames. If the receiver list is disabled, the filter elements are bypassed. Otherwise, the first matching filter element determines whether the frame will be accepted or rejected. When the receiver filter is disabled or no filtering elements have matched, the frame is either accepted or rejected. Once a frame is accepted, it is appended to the RX FIFO, provided there is available space. If the RX FIFO is full and blocking mode is enabled, the frame will be discarded. RX FIFO 0 and RX FIFO 1 can hold up to 3 elements each. Messages that pass the acceptance filter are directed to the respective RX FIFO as configured by the matching filter element. The read-only registers FDCAN RXF0S and FDCAN RXF1S provide the following information: the position of the put index, indicating where the next message will be stored, the position of the get index, indicating where the next message will be read, the number of pending messages in the FIFO, the status of whether the FIFO is full. The RX FIFO blocking mode is the default operation mode for handling messages in the RX FIFOs. When an RX FIFO reaches a full condition, no new messages are written into the corresponding FIFO until at least one message has been read, and the get index has been incremented. If a new message arrives while the RX FIFO is full, the message is discarded, and a message lost condition is triggered. In contrast, RX FIFO overwrite mode allows continuous message handling even when the FIFO is full. When a full condition occurs in this mode, the oldest message is discarded to make space for the next incoming message. Both the put and get indexes are incremented by 1 to reflect this update. Up to 3 transmission buffers, TX buffers, can be configured for message transmission. There are 2 modes of operation. In TX FIFO mode, messages are transmitted in the exact order they were prepared by the software, ensuring a sequential message flow. In TXQ mode, the 3 message buffers operate independently, with the transmission priority based on message priority. Messages with higher priority are transmitted first, regardless of the order they were placed in the queue. The FDCAN controller also supports transmit cancellation. To cancel a requested transmission from a TXQ buffer, the software must write a 1 to the corresponding bit in the TXBCR register. Note that transmit cancellation is not applicable in TX FIFO mode. The FDCAN controller includes a TX event FIFO to manage transmission event handling separately from message transmission. This allows for efficient processing of transmit status information independently of the actual message data. Each TX buffer only stores the message being transmitted, while the transmit status, such as the success or failure of the transmission, is stored in the TX event FIFO. This design is particularly beneficial when operating with a dynamic transmit queue. Once a message is successfully transmitted, the TX buffer can immediately be reused for a new message, without needing to store or process the transmit status information first. However, if a transmit event occurs while the TX event FIFO is full, the event is discarded, and an interrupt flag is set to signal the overflow condition. The FDCAN controller peripheral provides 2 independent interrupt lines. This slide presents a comprehensive list of possible interrupt events that can be triggered by the FDCAN controller. This slide provides an overview of the low-power configuration modes available for the FDCAN subsystem. In stop or standby modes, the device is unable to perform any communication tasks. To avoid data loss or communication issues, it is crucial to ensure that all ongoing CAN traffic is fully completed before the peripheral transitions into either of these low-power modes. While the CPU core is in debug mode, such as when it is stopped at a breakpoint, the FDCAN peripheral continues to function normally. This includes ongoing reception of messages, which can potentially lead to reception overrun errors if the RX FIFOs or buffers fill up. Furthermore, registers that are categorized as reset on read or set on read are disabled in this mode. This means that reading these registers will not affect their values. For additional information, refer to the training for these peripherals, which may affect FDCAN behavior. Reset and Clock Controller, or RCC, for more information about the CAN clock control, and enable reset. Nested Vectored Interrupt Controller, or NVIC, for more information about the mapping of the FDCAN's interrupts. General Purpose IOs, or GPIOs, for more information about the FDCAN's input and output pins. Debug support, or DBG, for more information about the FDCAN's behavior when the CPU is halted. Application notes covering the CAN topic are available on st.com. To learn more about the CAN interface, you can also visit a wide range of web pages discussing the CAN communication protocol and bus monitoring tools. Many digital oscilloscopes support direct reading and analysis of data transmitted over the CAN bus. Thank you for attending this presentation.